All right, this is Mr. McMurray on an early Monday morning, and it's about 6:30. We're getting on with it here. Okay, about 6:45, but hey. Anyhow, we're on with more force notes. And so let's start with contact forces. We talked about this, I think, last time. Forces that touch an object to exert a force are the contact forces. Friction, things have to hit. Air resistance, which is friction between the air and an object moving through the air. You could also throw in water drag, which is the same thing, but just happening to something moving through water, and any kind of force that's applied when one object hits another object, okay? Non-contact forces or long-range forces are forces that can be exerted on objects that are not touching. And we talked about, or maybe we did, I think we did, about magnetism, okay? These repel each other. If I flip them around, then they will attract each other, even though they're not touching, okay? For example, I can put that one on top of my hand and I can make it move around. I don't think you can see that, but anyhow. There we go. Okay. It's slipping. Why? Because of the one underneath it without actually touching it. So non-contact forces would include electricity and magnetism, which are very closely related. We'll be seeing them a lot together. And gravity, of course, because although we are touching the Earth, that's not what causes the gravity. Gravity doesn't touch us and exert that on us. The moon is moving around the Earth, and it also is affected by gravity, but obviously it's not in contact with the Earth, or the Earth in contact with it. So those are non-contact. Now, tension forces are anything that we pull on. If you pull on a rope, pull on a chain, and it has anything else for that matter, there's tension, it straps tight, it's under tension, hence it is called a tension force, or that would be F with a T next to it would be the symbol for that. Okay. Now, the main thing about tension forces is you can pull things with a rope, but you can't push things with a rope. Okay. If I have my dog on a leash, I can hold him back if he tries to go too far, but if he comes toward me, then it gets all slack, and I can only force him to go where I want him to if I shorten the rope so it's tight, okay, and it's under tension. So basically, one of the main things about a tension force is that it is always a pull, never a push. Is it a push over? Well, all right. Now, besides tension forces, let's go on with some other things. Let's start about Newton's 3 laws of motion. Okay, we talked a little bit about forces and stuff. Now let's talk about some laws that govern motion and forces. Okay. All right, the first one we're going to say is Newton's first law of motion, otherwise known as the law of inertia. We'll talk about inertia here in a minute. And you've probably heard this one: objects in motion stay in motion, objects at rest stay at rest. However, that is only half of the law, so we need to make sure we know the rest of it. For example, all objects in motion will stay in motion at a constant velocity. Okay, a constant velocity means they're not speeding up, they're not slowing down, and they're going the same direction. Those three things have to be true to be at a constant velocity. So another way to say that is it must be going in a straight line at a constant speed. It cannot change direction, cannot change its speed. And so objects in motion will keep going just forever and ever and ever off in the same direction, okay? So that's the first part. All right. Objects at rest remain at rest unless an unbalanced or a net force acts on them, okay? All right, now, so here's the deal. Objects in motion stay at motion at a constant velocity unless an unbalanced force acts on them. And objects at rest remain at rest unless an unbalanced force acts on them, okay? And that will cause some kind of change or acceleration in their motion, okay? Remember, acceleration can also mean slowing down. So that's basically all we're saying right there. All right. So they're just going to keep on going how they are. If they're at rest, they're just going to stay at rest unless something happens to change that. Okay, if they're moving at a constant velocity, they're going to keep doing that unless something changes that. Okay, now most objects, or that's what basically Newton and Galileo before him said, is that objects don't want to change. They want to just keep on doing what they are doing, which is what this law is really saying. And he gave a name to that. Actually, Galileo did way back before, but then Newton, about 100 years later, kind of quantified it and gave more information about it. He called it inertia is the tendency of an object to resist any change in its motion. In other words, objects at rest want to stay at rest. Objects that are moving at a certain speed want to just keep on moving at that same speed. They do not like change. Okay? All right. So we need to do some examples of that, but let's do one more thing. Inertia then really just depends on the mass of an object. Okay? Inertia depends solely upon the mass of the object. The greater the mass, the greater its inertia. The less the mass, the less the inertia. So, for example, if I have a semi-truck that's going 60 miles an hour down the road, and I have another semi-truck that's just parked on the side of the road, which one has more inertia? Well, it's exactly the same. Now, I'm not suggesting that the effects on you, for example, will be different if you step in front of one going 60 miles an hour or one parked on the side of the road. But as far as inertia, it's going to be just as hard to get it started as it would to make it stop, because inertia, changing the motion of an object, only depends upon the mass of the object. All right, now let me get some examples and we will do some demos. All right, first example, if I have this bowling ball, okay, if I put a force on it, that's only when I first am touching it. Notice as soon as I let go of it, there is no force acting on it. Okay, that's just, it has motion, but it doesn't have force. Force is something that's applied to it, so I put force on it. Now, once I put a force on it, it just keeps going and going and going because I'm not putting any force on it. Now, there is a force on it, that is gravity's acting on it, okay? And when it hit the chair leg there, that was another force acting on it. But basically, since there are no forces acting on it, it will just keep going forward in a straight line motion, okay? And this is primarily because there's very little friction or air resistance. Technically, there's a little bit of each of those, but for practical purposes, we can say that there's not. And it would just keep on going until it runs into something and another force is acted on it, okay? All right, here we are again. Let me get a little bit closer here so you can see this maybe. All right, we have 3 golf balls here on little tubes with a tin pen, and underneath each one we have a ball of water. Okay, now if I jerk this fast enough and do it right, we'll see what happens. All right, and notice we have 1, 2, and 3. All 3 balls landed in the water, which means we did it right. All right, very good. And what happened is we're pulling it out. So when we pull it out really fast, I'm not exerting a force on the balls. I'm exerting a force on the pan, which hits the little cylinder things that they were on, exerts a force on them, but it does not exert a force on the balls. So while the pan and the clear cylinders went flying this direction, the balls, because they had inertia, did not change their motion, just fall directly down, because now there's no longer the normal force of the little cylinders pushing up on them to counteract gravity, and so they plop down into the water. All right, very good. We'll stop right there. All right, so those are just some examples of inertia, but let's move on to Newton's second law of motion. Newton's second law of motion does not have a catchy little saying, object in motion, stay in motion, or Newton's third law, for every action there's equal opposite reaction. And so therefore it kind of gets lost because it's a little wordy. And basically it comes down to a formula here, F equals M times A. Or to rearrange it, and the way he actually originally wrote the law would be acceleration is equal to the net force. Remember, you have to have a net force in order to have acceleration divided by the mass. In other words, he said basically how much something speeds up or accelerates has to do with how much force is acting on it divided by how much mass is acting on it. All right, and Galileo before him, and then Newton also explained this because it was believed for a long time that if you had 2 heavy objects that they would fall at different rates. The heavy object would fall faster and the lighter object would take less time. Okay, and this was still, a lot of people would probably disagree with this because they think, oh no, heavier things fall faster. Now, it is true, for example, if I take a piece of paper and I drop it at the same time as a ball, which one is going to hit the ground first? Well, probably the ball, right? Because the piece of paper is going to have air resistance, okay? Now, let me try this again, see if I can get here where we can get the ground in it. Okay, if I take two objects that are about the same air resistance, so I got these two balls, okay? If I drop them at the same time, I don't know if you can see that, but they hit at almost exactly the same time, okay? And so, turned out Galileo was right, and Aristotle and some of the earliest scientists were wrong when they said heavier objects fall faster, okay? Well, why is that? Why do heavier objects not fall faster? Because which one has more force of gravity pulling on it? Well, the heavier object does, okay? The heavier object has more net force, okay? So that's the first part of the equation. However, it also has more mass, and we just learned from the first law, that means it has more inertia or more resistance to moving. And so even though there's a greater force of gravity acting on it, there's also a greater resistance to start moving, and so that cancels out and it ends up accelerating at the same rate as the little ball. Because the little ball has a less force of gravity because it doesn't have as much weight, okay? Which basically the force of gravity is weight, okay? So there's less force acting on this one, but there's also less mass to resist the change in movement. And so the two balls will end up falling at the same rate. Okay, notice we're not saying the force of gravity is the same. They're not. This one has a big force of gravity, this one has a small force of gravity. But because this one has a big mass, it also has more resistance. It has a little mass, it has less resistance. And that's basically what Newton's law here showed, is how that could be true, that all things are going to accelerate or speed up at the same rate as you drop them. Now, if you have something like this piece of paper, on the other hand, now it's going to fall very slowly. Why? Well, because it has a lot of surface area and basically a type of friction, and so it's not going to fall very quickly. But as long as you have objects that have roughly the same amount of air resistance, same shape, and roughly enough the same size, then that's not going to be an issue. Okay, so if you don't include air resistance, then everything will fall at the same rate. All right, and that's basically what Newton's second law is. And he really just broke this down. Basically, if the force is on top, if the force increases but the mass stays the same, then what's going to happen? Well, this number gets bigger, this number stays the same, the acceleration is going to get bigger. And so what that in fancy words would say, acceleration is directly proportional to the force that's applied to it. And we should probably put net force right there. So if you want to put net force, acceleration is directly proportional to the net force applied. Remember, if it's a balanced force or net force is 0, then that's not going to make it accelerate, not going to change, right? Okay, now the other thing is, say the force stays the same, but the mass increases, then it's not going to accelerate, okay? If I push these two balls down the road with the same amount of force, the bigger ball is going to accelerate slower because it has more mass, more resistance than this one, okay? All right, so acceleration is directly proportional to the force applied, all right? And so, but it's going to be indirectly or inversely proportional to the mass of the object. In other words, if you have a big mass, you're going to have a small acceleration, all right? And so more force, more acceleration, less force, less acceleration, more mass, less acceleration, less mass, more acceleration, assuming you're getting the same amount of force, okay? Now to remember, if the net force is 0, then either there's going to be net force 0, this is 0, that means this acceleration is equal to 0. So either it's going at a constant speed, Newton's first law, all right, or it's at rest, all right, because it's not going anywhere. That's a constant speed of 0. And if the net force is greater than 0, then it will have some acceleration because everything has some mass, okay? And that's basically what Newton's second law talks about and comes right down to. All right, that's some information about the two laws. We'll have some more notes later, but that'll do for now. Have an excellent Monday.